thank you for having me here today. And thank you all for joining this talk. Today, I will be talking about the complexity of robust proper learning of half spaces with agnostic noise. And this is based on two papers, both of them co-authored with Ilias Diakonikoulos and Daniel Kane. For the simplicity of the presentation, I will not distinguish these two papers. So if I say that a result is from this work, it means that it comes from one of these two papers. Since this talk is aimed towards the parameterized algorithms and complexity folks, I will first review some basic definitions and notations from the learning theory front. Specifically, there are a lot of terms in the title here, both learning, proper, half space, agnostic noise, and robust. So we will go through each of them. We'll start with the probably approximately correct or PAC learning. There are the following terminologies that we use throughout. So there is an instance space or a sample space X. A hypothesis class is simply a set of functions from this instance space to plus or minus 1. A label sample is a pair X, Y, where X is from the instance space and Y is the label, which is from is either plus or minus 1. And for a hypothesis little h, we say that it correctly classifies a label sample X, Y if Y is equals to HX. In PAC learning, there is an unknown distribution D, which is on the set of label samples. Furthermore, we assume that there is a hidden hypothesis little h star that correctly classify all the label sample in the support of D. So our algorithm will not be given direct access to this distribution. Rather, what we are given are samples xi, yi, which are independently drawn from this distribution D. Furthermore, we are also given a positive real number epsilon greater than 0, which is our accuracy parameter. So our goal is to output a hypothesis that does well on this distribution. What do we mean by does well? To quantify this, we also have to define the classification error of a hypothesis H with respect to the distribution D. So this is simply the probability that if we draw X, Y from D, H will not correctly classify the label sample X, Y. Now note here that the H star has classification error 0 from our assumption that it correctly classifies all points in the support of D. We will not be able to get the classification error to be 0, but our goal here is to get the classification error of our output hypothesis H to be at most epsilon, the accuracy parameter. And this we want to happen with high probability, let's say 0.99, for example. Now, one thing to note here is that the output hypothesis H is not necessarily from the hypothesis class big H. So you can output, actually, you are allowed to output very complicated hypothesis H, but this might not be desirable in general because this complicated hypothesis can be hard to interpret. So this leads to the definition of proper learning. So a learning algorithm is said to be proper if the output hypothesis H belongs to the hypothesis class big H. In this talk, we will be focusing on only the proper learning algorithms. We will come back to discuss about improper learning algorithm a little bit at the very end. Finally, let us refer to this assumption that there is a hidden hypothesis that correctly classify all the points as the realizability assumption. This is to distinguish between this PAC learning setting and what we will discuss next, which is the agnostic setting or agnostic PAC learning model. So this model is almost the same as before, except that we don't have the realizability assumption. In particular, the distribution D can be any arbitrary distribution on the set of label samples. Once again, the inputs are the same as before. We have a list of samples and a positive real number, the accuracy parameter epsilon. Now, of course, here we cannot hope to output a hypothesis with classification error at most epsilon because it might not even exist at all. So instead, we have to compare it against the optimum classification error, denoted by op here, which is just defined as the infimum among all the possible error among all the H in the hypothesis class, big H. And for readability, sometimes I will drop D and H from this notation. There will be no ambiguity, so don't worry about it. Now, our goal here would be to output a hypothesis class H such that the error, the classification error is at most alpha times the optimum plus epsilon, where alpha is some constant greater than 1, which is the approximation ratio. Okay, so that's the agnostic PAC learning model. Everything we have discussed so far has been pretty abstract. So let us now be a little bit more concrete. Specifically, in this work, we will be focusing on the half spaces. So the instance space of the half space is just the d-dimensional, all the d-dimensional points. And for W in R to the D, we define the half space SW as the hypothesis that classify X based on the sign of the dot product between X and W. So if X dot W is greater than or equals to 0, this is 1. If X dot W is less than 0, this is -1. For example, if this is the W, the hypothesis class would look like this. So on the one side, it will classify one side to be plus and the other side to be minus. And the class of the half space hypothesis is simply the class of all of such half space for all W in R to the D. Okay, so our problem can now be stated as follows. So we have a distribution in R to the D times plus minus 1. And we are given a bunch of samples drawn independently from this distribution and positive real number epsilon. And we want to output a half space such that the classification error of this half space is no more than epsilon plus alpha times the optimum. For example, here might be our distribution D. So if this is a distribution D, then this W star would be the optimum and it misclassifies 2 points. So the op is 2 over the total number of points. And maybe if our algorithm output this W instead, then it misclassifies a total of 4 points. So if we ignore epsilon for a moment, we will get an approximation factor of 2. Now, unfortunately for us, this problem is very hard. Specifically, it's NP hard for any constant factor approximation. And in fact, this hardness holds even for approximation factor that is near polynomial in D. Okay, so that's hard. So we will be looking at some different kind of relaxation of this problem. To introduce the relaxation, we have to discuss the last part in our title, which is adversarial robustness. Just in case some of you have not seen this before, I will give just a very quick informal intuition. So the notion is based on the so-called adversarial attacks. So these are attacks where the attacker try to move a point X to some other point C, where C is close to X in some metric, in order to flip our classification label from correct to incorrect. A well-known example here is in image classification. For example, if we have an image X, which is a panda, let's say, and our classifier classify it correctly as a panda, it has been shown that sometimes it's possible to just change the image a little bit and make the classifier classify the image to something else completely different, like a worm or something like that. Even though to human eyes, these two images, X and C, are completely the same. So what we want is that we don't want the adversary to be able to execute such an attack. Specifically, we want our classifier to be robust against such an attack, and we will define next what this actually means. And the closeness metrics that we will use are LP matrices. In literature, the most commonly studied are the case where p equals to 2, so the Euclidean norm, or p equals to infinity, or the L-infinity matrix. So these two are worth keeping in mind. All right, with the informal intuition in mind, we can now define formally what a robust error means. So for an LP matrix and for robustness parameter gamma, we define the gamma robust error to be the probability that if we don an xy from D, if the adversary execute this attack where the adversary can move x to any c within the LP ball of radius gamma, it can make the label incorrect. Or in other words, there exists C such that C and X are gamma close in the LP metric such that HC is not equals to Y. Just to give you an example, in L2, right, if this is our distribution D and if this is our W, the standard notion of classification error will say that this half space has 0 classification error. However, if we look at the gamma robust error, the adversary can pick any point that is within radius gamma to that particular point. And if the adversary can flip the label to the incorrect label, that point is also counted as incorrectly classified. For example, this plus point that is highlighted is now counted as an error in the gamma robust error notion. And similarly, for these 2 minus points on the left. And for other LP metric, it's pretty similar, but instead of drawing an L2 ball, we are drawing an LP ball. For instance, in L infinity, we are drawing an L infinity ball, which is simply just a box. And as a notation here, we will write op of P gamma to denote the optimum gamma robust error among all the half spaces. All right, so with all the definition in mind, we can attempt to define the problem that we want to solve. So again, we have an unknown distribution D on R to the D times plus minus 1. And we are given, once again, a bunch of samples from this distribution D and the accuracy parameter epsilon. And additionally, we are also given the robustness parameter gamma. Our goal here will be to output a half space HW such that with high probability, our gamma robust error of W is no more than alpha times op plus epsilon. However, this definition is not quite the right definition that we want to solve yet. And the reason is that the margin gamma is pretty meaningless if we don't bound the norm of XP. Because if we let the sample X to be extremely large, then even if we set gamma parameter to be 0.5, we have to sort of scale it down based on this X, the norm of X. And hence, it doesn't really tell us much. And more formally, it's actually possible to show that under this particular definition, the problem is still as hard as the agnostic PAC learning of half space, even for any gamma. So we have to change our problem a little bit. And the change is not too hard. In particular, we just limit the P norm of X. So we just ask that the distribution is instead of on R to the D times plus minus 1, it has to be on the unit LP ball in D dimension times plus minus 1. So each X has LP norm at most 1. Okay, now, so this is the second definition, second attempt at defining this problem. It turned out that this is still not quite the right problem to study just yet. So this second hiccup is a little bit more subtle, but roughly speaking, if we want our gamma robust error to be small, and we are comparing with the optimum gamma robust error as well, it turns out that there is not enough slack to make the problem easier. So this problem that we are staring at is still as hard as the agnostic learning of half space, which, as we said earlier, is NP hard. It was proved by Aurora et al. So we will relax this a little bit further. And specifically, the relaxation is that instead of requiring the the output half space to have small gamma robust error. We only require it to have small 0.9 gamma robust error. Okay, so this is the problem that that we want to solve. Okay, so if so we have some unknown distribution from LP unit LP ball in D dimension times plus minus 1, and we want to find a half space that has a small 0.9 robust error compared to the optimum gamma robust error. Okay, is this problem clear to everyone? Is there any questions so far? Okay, if not, I will continue. So having stated our problem, let's now look at what is known and what we show. So let me first go through the algorithm, and then we'll go to the lower bound later. So previous work by Ben David and Simon shows that it's possible to achieve approximation ratio 1 in the case of L2 robustness, so P equals to 2, where the algorithm running time is polynomial in D times 1 over epsilon to the gamma square. Okay, so this is pretty nice. However, the algorithm is slow when epsilon is small. I guess if you want to think about 1 over epsilon as like the problem size and 1 over gamma as the parameter, this is not FPT yet. So what we show, however, is that if we allow a little bit of approximation ratio, specifically it can be anything arbitrarily close to 1, but in this presentation I will just write 1.1. It's actually possible to do this 1.1 approximation in time poly in D over epsilon times exponential in 1 over gamma square. So in other words, in this viewpoint is kind of FPT in the parameter of 1 over gamma. And this, but this is for finite P, so this is for P less than infinity. For the case of P equals to infinity, it turns out that the running time is a little bit slower. The second term becomes D to the 1 over gamma square. Okay, so those are the algorithms. In terms of the lower bound, it turns out that all of these are basically tight. So first we show that in the setting of approximation ratio exactly 1, this 1 over epsilon to the gamma square is necessary. You cannot speed this up, assuming ETH. In the second case, where P is a constant greater than or equal to 2, and we allow any constant approximation ratio, we assume, we show that this exponential in 1 over gamma square cannot be significantly speed up. So you cannot get exponential in 1 over gamma square, gamma to the 1.99. And lastly, in the P equals to infinity case, and for some approximation ratio, specifically 1.5, for example, we can show that actually the D to the 1 over gamma square is necessary. So in this sense, if we think of D as the input size, then the P equals to infinity is not FPT versus the case of constant P is in FPT. Okay, so those are the results. So now we'll move on to see some of the proofs. And before we see the proof, let me just very quickly make 2 quick notes. So this will be 2 things that are good to keep in mind when seeing the proof. So the first note is about adversarial robustness versus the notion of margin of the half space. So in the margin notion, for an LP norm, we say that half space W correctly classify XY with margin gamma if Y times W dot X divided by the dual norm of P of W is greater than or equals to gamma. So in other words, you cannot just correctly classify the point, but your W dot X has to be also at least the gamma times the Q norm. And this Q norm is really nothing complicated. It's just a normalization once again, so that this term is between -1 and 1. So that again, we can talk about margin that is between 0 and 1. Now, this is our gamma robust error that we defined from before. It turns out that this notion is the gamma robust error is exactly equals to the probability that W does not classify XY with margin gamma. So in this sense, we will sometimes use the word gamma margin error in place of gamma robust error. And just to give you an illustrative an illustration, so here is the picture that we saw before for the gamma robust error. So if you think of the margin, it is more like we take the strip of width 2 gamma, and everything in that strip we also count as incorrectly classified with margin gamma. And these two notions, as you can see, are the same. Okay, so that's the first thing I want to note. Second thing I want to note is the similarity and differences between learning and empirical risk minimization, or ERM. So learning is what we just what we had seen before, where there is an unknown distribution D. The difference between learning and ERM is just that in ERM there is no such unknown distribution. So we are given input samples, and our error and the optimum are defined with respect to the input samples, so not with respect to the underlying distribution. So it turns out that these two problems are actually equivalent. So on the one hand, if you have a PAC learning algorithm, you can get ERM algorithm pretty easily by defining D to be the uniform distribution over your input samples. And the opposite direction is what is known as generalization bound. It's not too important for us here, but basically, if we can solve ERM for a certain number of sample M, we also solve the PAC learning problem. So these two are equivalent, and it will be more convenient to think about the ERM problem in general. Okay, so having those two in mind, let us go to our algorithm. So recall again, in our algorithm, we want 1.1 approximation. And for P between 2 and infinity, the running time will be exponential in P over gamma square. For P equals to infinity, the running time will be D to the 1 over gamma square. All right, so the algorithm will actually be extremely simple, but I will have to introduce one more notion. I know that it has been a lot of notion, but this is basically the last notion, so please bear with me here. So this is the notion of online learning of half space with a margin. So in the online learning setting, the setting is as follows. So there is, you can think of it as a game that goes on in infinite round. And at the start of round T, the learner has some current half space WT. And the learner is then given a sample XT, but without the label. And the learner uses WT to classify XT. Then once this classification is done, the true label YT is revealed to the learner. The learner can then use this information to update the hypothesis from WT to WT plus 1. Now we say that the learner makes a gamma prime margin mistake in round T if the point XT, YT is not correctly classified by margin gamma prime. So to get some reasonable mistake bound, we will also have to assume some assumption. And specifically the assumption here is that in all the sequence XI, YI, there is actually a hidden half space W star, which the learner doesn't know, that actually classify all the points with margin gamma. So we will call this a gamma margin assumption for short. So now we can define gamma prime learner with mistake bound M. So we say that a learner is a gamma prime learner with mistake bound M if under the gamma margin assumption, the learner make at most M gamma prime margin mistakes in total, even if we run this infinite round. Okay, so many of you might have seen this perceptron algorithm before. So the perceptron algorithm is a pretty basic algorithm where if you do not correctly classify xt, then you just update your w by adding the label yt times xt to it. And a classic theorem from the 60s says that the perceptron algorithm is gamma 0 learner with margin bound 1 over gamma square. And it turns out that there is a kind of margin version of this perceptron where you don't only perform update when you misclassify the point, but you perform update even when you do not classify the point with enough margin. And in this case, you will have that you can this margin perceptron algorithm is a gamma prime learner with a mistake bound that is 1 over the difference between the two margin square. But the perceptron algorithm and also the margin perceptron algorithm only works in the L2 case. For the other LP case, gently generalize those algorithms, and he gets a mistake bound of P over the gap between the two margin square in the case where P is less than infinity. When P is infinity, the mistake bound become log B over the difference between the two margin square. Okay, so those are the known results about the online learning with a margin. Now I can state what we actually prove, which is actually a pretty simple lemma, as you will see in a moment. So what we actually prove is that you can take an online learning algorithm and convert it into a robust agnostic learning algorithm for half space. Specifically, our lemma says that if you have a gamma and 0.9 gamma learner with mistake bound M, you can turn it in to a 1.1 approximation for agnostic robust learning of half space, where the running time is exponential in M, where M here is the mistake bound, the number of mistake, the number of 0.9 gamma mistake that the algorithm makes. Okay, so you prove this lemma, and as I promised, it will be very simple. Before we prove that, let's note here that this lemma, together with the gently result that we mentioned earlier, already imply what we claim. Specifically, it implied the 1.1 approximation for P between 2 and infinity that run in times exponential in P over gamma square. And in the P equals to infinity case, it runs in time D to the 1 over gamma square. All right, so let's prove this lemma. So as I said earlier, it will be simpler to consider the ERM version of the problem. So let's consider that. And instead of giving you an algorithm that succeed with high probability like 0.99, I will instead give you a polynomial time algorithm, but it will succeed with probability only exponentially small in M. However, from this, we can easily get our lemma because we can just repeat this algorithm exponential in M times and pick the best half space that we see in all those runs. Okay, so what does this algorithm looks like? So this algorithm works as follows. So let A be our gamma 0.9 gamma learner with mistake bound M. We will run the following for M rounds. So for each round, we randomly pick a sample xt, yt among the samples which are not correctly classified by WT with the design margin 0.9 gamma. And then we just feed this xt, yt to A, and A will update the hypothesis from WT to WT plus 1. And then at the end, we will just output the best half space WT that we have considered so far in our algorithm. Okay, so that's the entire algorithm. As I said earlier, it's pretty simple. There is nothing complicated here. Okay, so let's very quickly prove that this gives us a 1.1 approximation with probability at least exponentially small in M. So to prove this, let us define very quickly two notions. So let us call W star the optimum half space. So this is the half space that classify all but optimum fraction of samples with the margin gamma, and let S star be the set of sample for which W star doesn't correctly classify with margin gamma. So in particular, S star has size at most of fraction of all the samples, all the input samples. Okay, so how do we prove this? So first of all, if at any point in our run, if the 0.9 gamma margin error of WT is less than or equal to 1.1 op, we are completely done. So that's just by definition. Now, if this error is larger than 1.1 op, what does this mean, right? So this means that when we randomly pick a sample xt, yt, we are picking it from 1.1 op fraction of points, but S star only contains op fraction of samples. That means that the probability that xt, yt is not from S star is some constant greater than 0. So this means that since we run this M round, the probability that we never pick anything from S star is at least exponentially small in M. Now, when this happens, when we doesn't pick anything from S star, then since A already misclassify M points, and all the points that we feed in are actually correctly classified by W star with margin gamma, the guarantee of A actually imply that the Wm plus 1 will correctly classify everything that W star also correctly classify, I mean with margin gamma. And by definition, this means that the 0.9 gamma margin error of Wm plus 1 is less than or equal to optimum. So we are also good in this case. So that's basically it for the proof of the algorithm. Are there any questions so far before we go forward to the hardness section? All right. If not, then I will continue to the hardness section. Okay, so we have 3 lower bounds. So I think due to time constraint, maybe you will be able to only go through the first one, but let's see. So let's first try to prove this first low bound, that is which is for the case of p equals to 2 and approximation ratio 1. So for exact. So we want to prove a low bound of the form exponential in omega of log 1 over epsilon over gamma square. Okay, so this is what we want to prove. So how would we do this? I mean, we will do a reduction from our favorite problem, k-clique, and we reduce from k-clique to the robust ERM for half space, where the margin gamma will be 1 over square root k. The dimension and the number of samples D and M will be linear, will be polynomial in N. And also in the yes case, we have that the gamma margin optimal error is at most theta for some theta. And in the no case, we will have that the 0.9 gamma margin optimum error is at least theta plus some poly in N. In other words, we will have epsilon equals to some poly in N. So since we know that the k-clique problem cannot be solved in n to the little o of k time, we immediately get the lower bound of 1 over epsilon to the omega of 1 over gamma square, because here 1 over epsilon will be poly in N and 1 over gamma will be square root of k. Okay, so that's our goal. So let's proceed to the reduction. Yeah, one thing to note here is that actually the no case is stronger than what I stated earlier. In particular, it holds not only for the 0.9 gamma optimum, but also for the optimum without any margin at all. So even if you don't require any margin, you still have to suffer this theta plus poly in 1 over poly in N error. Okay, so this is what we want. So we will reduce from the k-clique problem. So let's say the vertices we want to be in here. So we will have d equals to n plus 1 coordinates, where we view each coordinate, each vertex as one coordinate. And we also add an additional coordinate, which I call now. So before we see the reduction, let us take a look at the intended solution. So in the intended solution, we want the following. We want our half space W to have value 1 over square root k, 1 over square root k plus 1 at the coordinate now, and also at all the coordinates that correspond to the vertices in the k-clique. Now, here is an example. So if our k is equal to 3, and this is our 3-clique, V3, V4, V5, then our half space W will have to look something like the one on the right here. And note here that by construction, the L2 norm of W is equals to 1. So we will not have to worry too much about the normalization factor here. All right, so let us now take a look at the how we construct the sample. So there are 3 types of sample. The first type is what we call non-edge sample. So for every non-edge U and V, we create n copies of the following samples. So for the vector x, we set the null coordinate to be minus 0.6. We set the coordinate of U and V to be both 0.5, and the other coordinate we set to be 0. And then we let the label be minus 1. The next type of sample is the vertex sample. For every vertex V, we create a sample where in the null coordinate, we set it to be minus 0.4. And for the V coordinate, we set it to be 0.5. And everything else, we set it to be 0. And the label here is 1. And finally, we have a null sample. So this is just a sample that we set the first coordinate to be minus 1. And then we set the label to be minus 1 as well. Finally, we set our target error data to be n minus k over m, where m is the total number of samples. In other words, this means that in the yes case, we are allowed to misclassify n minus k points with respect to margin gamma. And our gamma will be order of 1 over square root k, specifically 0.1 over the square root of big K, where big K equals to k minus 1. K plus 1. And again, all these samples lie in unit L2 ball, so we don't have to worry too much about normalization here. Okay, so having defined the reduction, let's check the yes case. So I just copy the intended solution in the yes case here. Recall again that we just set the null coordinate to be 1 over square root k plus 1, and every coordinate corresponding to the k-clique to also be 1 over square root of k plus 1. So for the non-edge sample, since we never pick both U and V when U and V is a non-edge, we will only have 0.5 over square root k from either U or V, but we will have minus 0.6 over square root k from the null coordinate. So indeed, we correctly classify this point with margin gamma. And the last sample, the null sample, this is pretty obvious. We also correctly classify this point with margin gamma as well. How about the vertex sample? So for the vertex sample, if we do not pick V, then we will misclassify this point. However, if we pick V, we will get 0.5 over square root big K from V and minus 0.4 over square root big K from the null. And we will correctly classify this point with margin gamma. In other words, in this case, for this setting, we exactly misclassify n minus k vertex sample exactly for those vertices that are not in our clique. So this means that our gamma margin error is exactly equal to theta. All right, so that's the yes case. So now we will move on to the no case. Okay, so in the no case, we want to show that when the clique size, the max clique size at most k minus 1, the op in the ERM for half space has to be at least this theta plus some poly 1 over poly in n. Now first, let me know that this poly term, we don't have to worry about it. The reason is that we have only m samples anyway, and m is polynomial in n. So if optimum is greater than theta, is at least greater than or equal to theta plus 1 over m. So we can ignore it. Okay, so to prove this statement, let's prove the contrapositive. Specifically, we will show that if op is less than or equal to theta, then the clique size has to be at least k. Okay, so to see this, first of all, note that from our definition of theta, which is just n minus k over m, where m is the total number of samples, this means that in the optimum half space, which we call here W, we have to correctly classify all but only n minus k samples. Now, since we create n copies of the null sample, we cannot misclassify it. So we must have that we correctly classify it. So the null coordinate of W has to be greater than 0. So once this is the case, we can define the set C of vertices to be the set of all vertices for which WV is greater than, say, 0.7 times now, W now. And from the vertex sample, since we know that we are misclassifying at most n minus k sample, we have to correctly classify vertex sample for at least k vertices. But whenever we correctly classify the vertex sample, it means that the vertex has to be in this set C. So we have that the set C has size at least k. Now, finally, for each non-edge sample, again, since we create n copies of it, we cannot misclassify it. And what this means is that for any 2 points in C, there cannot be a non-edge. So C has to induce a clique. Okay, so we are done here. So we have that in the no case, there is in the no case, if clique size is less than k minus 1, the optimum has to be also greater than theta. Okay, so that's the first reduction. Are there any questions so far? Okay, so I have 12 minutes, so I will try to go over just some high-level overview of the other two reductions. So for the second reduction, recall that here we want to show a lower bound of the form exponential in 1 over gamma square, ignoring the lower order term. But we want approximation ratio that can be any constant factor. So it turns out that this proof is actually pretty similar to the previous proof, except that instead of starting from k clique, we can start from 2 CSP instead. And specifically, if we start from 2 CSP instant with n variable and sufficiently large gap, then we can get arbitrarily large gap for the yes and no case in the ERM problem for half space as well. But here the margin will be 1 over square root of n, where n is the number variable of CSP. And this reduction can be viewed as a modification of the Aurora et al. Reduction that I mentioned earlier as well. Now, since for 2 CSP, we know that for any constant factor, it's hard to approximate in time that is exponential in n to the 1 minus little over 1. This is by the nearly linear size PCP of Morse code with RAS. This indeed implied the lower bound of exponential of 1 over gamma square minus little over 1 for our problem as well, since now our gamma is 1 over square root n. Okay, so that's kind of all that I would say for the second reduction. So let's now move on to the third reduction, the one for p equals to infinity. And again, kind of the hard part for this p equals to infinity is that we somehow want this d factor to show up as well. So we want the running time lower bound of d to the 1 over gamma square, while also have some hardness of approximation. So for this reason, we will have to start from a hardness of approximation result. For this talk, I will just try to do something slightly different. So instead of wanting a lower bound of d to the 1 over gamma square, like on the left, I will try just d to the 1 over gamma, which is the one on the right. And for this d to the 1 over gamma, you can reduce from k set cover. Specifically, you can reduce from k set cover so that the margin parameter is roughly 1 over k. And the other things are pretty similar to before. Now, since we know that the k set cover is hard to approximate for any constant factor, we also get hardness of approximation for our ERM problem for half space as well, where the running time lower bound is now d to the 1 over gamma. Okay, so for the reduction itself, I will not go into detail here, but what I would say is that it's actually pretty similar to the reduction in the clique case. Specifically, previously for the clique case, we have this null sample, which in this case we still have. And we also have, previously we had the non-edge sample, which enforced that an edge is not picked. But now we will instead have a covering constraint. The only difference is the subset sample. So previously for the clique, we misclassify whenever we are outside of the clique. But here we will misclassify whenever we are in the set cover. And roughly speaking, the yes case will go very similarly to before. So we can check everything like similar to before, and we will have that the op is indeed what we want. However, the no case turned out to be much more challenging. And again, since I did not give this construction in detail, let me only say a few words about it. So it turns out that the challenge in the no case comes from the following. Even when the set cover instant is a no instant, where there is no small set cover size, there is no set cover of small size, there is still a trivial half space that actually correctly classify everything with the margin that we want. And this half space is very simple. Basically, it places the same mass on all the subset coordinates. So we have n coordinate, each one corresponding to each subset. This half space will put this 0.5 over n mass in each of these coordinates. Okay, so this is different compared to the yes case, where in the yes case we only put 0.5 over k mass on the k coordinates that correspond to the set cover. So basically, the ultimate challenge for this case is to distinguish between this good solution and a bad solution. So just to summarize, in a good solution, if we ignore the null coordinate for the moment, in the good solution we have k coordinates that has the same mass, order of 1 over k. And in a bad solution, we have n coordinates which have the same mass, which is of order 1 over n. So we want to somehow design some samples for which the good solution will correctly classify it, but the bad solution will not. And to design such a sample, we use the following trick, which is that if we let S be a random plus minus 1 vector, and we look at the vector V dot S, where V is some fixed vector, then the expectation of this V dot S square is actually just equals to the L2 norm of V square. Now, if we look at our good and bad solution, in the good case, the L2 norm is actually order of 1 over square root k, because we are placing the mass on k coordinate, equal mass on k coordinate. But in the bad solution, we put equal mass on n coordinate. So the L2 norm is actually 1 over square root n. So what this means is that from this observation, the V dot S in the good case will be roughly 1 over square root k, but V dot S in the bad case will be roughly 1 over square root n. And of course, n and k are very different since we are in the parameterized regime here. So this led us to an example where basically we take this V dot S and check whether this V dot S is greater than or equals to some small constant over square root k. And since in the bad solution, the typical value of V dot S is so small, the absolute value is only of the order of 1 over square root n, with high probability it will not be correctly classifying this sample. But in the yes case, since typical value of V dot S is order of 1 over square root k, we will have that with a pretty high some constant probability. We will be correctly classifying this kind of sample with the desired margin 1 over square root k. And so this is kind of the rough idea. So we will not be going into more details here. But one thing I would like to note is that in this what I call random sign trick, the margin that we get in the yes case is actually 1 over square root k as well, which is the margin that we want, because we remember that we want a running time lower bound of d to the 1 over gamma square, where gamma is the margin. So it turns out that you can use this trick kind of all the way to get from the margin of 1 over k to 1 over square root k by using this trick on the other samples as well. But this and by that, what I mean using this trick, I mean that basically you take a random plus minus 1 sum of the samples together to boost the gap up from 1 over k to 1 over square root k and get this desired lower bound. But we have to do this in a careful manner, because if we don't do this carefully, then the L infinity norm will blow up and we have to rescale. And once we rescale, our norm will go back to being small again, which is not good. And because of that, we have to start with some more structural problems. Specifically, we start from a variant of label cover. And for such label cover, the only hardness that we know of is from gap ETH. And that's why in our paper, we have to assume gap ETH instead of just ETH. Okay, so I think that's all I have to say for the reduction. So let me very quickly conclude here. So in this talk, we discussed about proper learning of half space with adversarial robustness in LP and in the setting where there is agnostic noise. Our main algorithm is that we, for p greater than or equals to 2 and less than infinity, we give a 1.1 approximation algorithm that run in time poly in d over epsilon and exponential in p over gamma square. In other words, when p is constant, this can be thought of as being FPT in the parameter 1 over the margin gamma. For the p equals to infinity case, we give an algorithm which run in time d to the 1 over gamma square. So in other words, if you think of d as a problem size, this is not FPT in 1 over the margin. And we also show tight running time lower bound for both cases. In terms of open question, I think the most interesting one to me is about improper learning. So as I said at the beginning of the talk, proper learning means that we output a hypothesis that is within this class, right? And with this class mean that we output a hypothesis which is a half space. And in our work, we always consider this. But you can consider outputting some other hypothesis that is more complicated, such as polynomial or like, you know, a linear threshold polynomial and so on and so forth. And it turns out that, in fact, it is possible to get a faster algorithm if you consider improper learning. But the known algorithm only works for p equals to 2, and the output hypothesis is not robust. So they only show that in this Shalev-Schwartz work from 2009, they only show that the classification error is small, but not the robust classification error. So it would be interesting whether you can get a similar result for the robust case as well. And even more challenging is the lower bound front. So it's, in general, it's very hard to prove lower bound for improper learning. So you often need some average case assumptions, such as, you know, random CSP is hard, or some cryptographic assumption. And these often don't yield very strong lower bound. For example, Daniel Lee actually shows a lower bound for improper learning of half space case, but the running time lower bound itself is only quasi polynomial in 1 over the margin. So which is very far from exponential in 1 over the margin square that we know. So it would be interesting if we can somehow push this lower bound forward. And of course, there are quite a few technical, like more specific open questions. Like one, for example, is to relax the ETH assumption, to relax the gap ETH to ETH in the case of p equals to infinity. And there are also others. All right, I think that's all I have for today. Thank you very much.
Yes, thank you very much also, Pasin, for a nice talk. So any questions, please? Okay, it doesn't look like there are any questions. Okay, then Pasin, thanks again. That was very nice. Yeah.
Thank you.
Thank you. Yeah, thank you. And bye.
Bye.